Hey everybody, in this video, we are going to continue talking about rate laws. The very first topic we are going to talk about is the effect of changing concentration on the rate. Now let's pretend that a reaction has a rate law that is defined by K times the concentration of X to the 0 times the concentration of Y to the first times the concentration of Z to the second. So, if we simplify all of this and turn it into an expression, we get that rate is equal to this value over here, which is K times the concentration of Y to the first times the concentration of Z to the second. And as you might know, the order of X is 0, the order of Y is 1, and the order of Z is 2. So this will be the generic rate law that we will base everything off of, and this will be the expression that we will use as a benchmark to compare the rates. And I'll show you how that works. So what happens if we double the concentration of X? Or in other words, we double the concentration of a zero-order substance. So if we do that, then instead of the rate law being the one above, it is going to be this. And instead of having just the concentration of X to the 0, you're multiplying the concentration of X by 2, and this will give you the new concentration, and this new concentration will, of course, be raised to the 0 power. And we know that after simplifying this, anything raised to the 0 is going to be 1, so essentially it is going to disappear, and in the end, we get that the expression is going to be K times the concentration of Y to the first times the concentration of Z to the second. Now this expression matches the first one, which means that the rate didn't change at all. So the same rate was maintained, and this allows us to conclude something. This tells us that multiplying the concentration of a zero-order substance by a constant such as 2 does not impact the rate. So in other words, rate is not related to concentration, which was the definition of a zero-order reaction, as we might remember. Now what happens if we double the concentration of Y? And Y is a first-order substance. So here, the concentration of Y is doubled, and this new concentration over here is raised to the first. And simplifying it, of course, this gets canceled out again because it's 2 to the 0. But this time, since 2 to the 1 is 2, then 2 comes out here. And notice how 2 times K times Y to the first times Z to the second is twice that of our original expression over here. So this means that the rate is twice as much as before. So this tells us something. This tells us that multiplying the concentration of a first-order substance by a constant multiplies the rate by the same factor. So we multiplied the concentration of Y by 2, and the rate increased by a factor of 2. So rate is proportional to concentration, and that's what first order means. Now, what happens if we double the concentration of Z, which is a second-order substance, as we discussed up here? So, if we do that, then our Z will be multiplied by 2, and all of this is the new concentration, so we will have to square that. And 2 squared is 4, and 4 comes out here because math. And then you see that this expression is 4 times as much as our benchmark expression, which means that the rate was 4 times as much as the initial rate, which was this one over here. And because of that, we can conclude that multiplying the concentration of a second-order substance by a constant multiplies the rate by the same factor squared. So we multiplied the concentration by 2, but the rate was multiplied by 2 squared, or 4. So rate is proportional to concentration squared. And you could write it like this: rate is proportional to the concentration of A squared. So, for example, if A doubles, then the rate will be times 4 because 2 squared is 4. So, now that we learned about this, let's use this knowledge to help us determine the order of reactions. So in this section, I want to teach you how to calculate the order from instantaneous rate versus the concentration of substances. So what I mean by this is that I will give you the concentration of the substances involved as well as the instantaneous rate, and you will calculate the orders from that information, assuming that there's enough information. So let's just say that our reaction is x to y. It's a very simple reaction, but the order is not 1 for both of them, because don't be deceived by the net reaction. That does not tell you the order. Remember, order can only be derived from either experimentation or from the mechanisms, and we could do it by experimentation, which is what we will do in this video. So, I have some nice data here. I have the concentration of x and the concentration of y, and the instantaneous rates. So, in our first row, we have 0.5 molar, 0.5 molar, and the rate is 2 molar per second. Great. Now, what about the second row? Well, we changed the concentration of x, so we went from 0.5 to 0.8 molar, but we kept the concentration of y constant, and it turns out the new rate is going to be 5.1 molar per second. So, as you can see, our y is kept constant because the concentration was multiplied by 1, and for any order reaction, if you keep these concentrations constant, that means that there will be no effect on the rate, because if you keep something constant, the rate will be constant. But if things start changing, then you could determine some things. So we see that while our y is staying the same, which means that that won't affect the rate, our x is not staying the same, and this may or may not affect the rate depending on the order. So as you can see, we multiplied the concentration by 1.6, and the rate was multiplied by 2.55, or 1.6 squared. And if you know what's going on, you know what's going on, because we multiplied the concentration by 1.6, and the rate was multiplied by 1.6 squared. This tells me that x, the thing we are changing, has a second order. So I concluded right away that x is going to be equal to 2 in the rate law over here, because x is second order according to our data. Now, this is a good way to do it. It's called the eyeball trick, coined by myself. And if you don't like that trick, that's fine, because I have an algebra trick for you. So we know that rate is equal to k times the concentration of x to the x times the concentration of y to the y. So we simply plug in as much information as we can. So we have our rates, of course, and we have our concentrations of x and y, so I plugged in those. But we don't know what k, x, or y are, so those are our variables. Now what you can do, especially when this is constant, you can actually divide these two equations and treat it like a system of equations. So I divided both of them, so if you divide two of the same things, then they cancel out. K divided by k cancels out because it equals 1, and we are left with 2.0 divided by 5.1 gives us 0.39, and this is equal to 0.5 divided by 0.8 to the x. And this is an exponent rule, because if you divide 0.5 to the x and 0.8 to the x, you essentially can combine the things inside as long as the exponents are the same, and you end up getting 0.5 over 0.8 to the x is equal to 0.39. So, doing some math, we can see that 0.39 is equal to 0.625 to the x, and this looks like some logarithm problem. So we are going to do logs, and we can see that the log of the base, which is 0.625, of 0.39 is equal to x. And if you know your log rules, you do your log rules. So log of 0.39 over log of 0.625 is equal to x. And note that on most calculators, when you see a log without any base, it usually is base 10, and that's fine. So we do the math, and we see that 2 is equal to x. So that's what we predicted before, and it turns out either method works for predicting the order of x. Now let's figure out what the order of y is. So let's compare rows 1 and 3, because in rows 1 and 3, the x stays constant, which means that x will not be impacting our rate. Instead, only y will be impacting our rate, and we want to see how it does that. So as you can see, 0.5 to 1 is times 2, and look at the rate, it went from 2 to 4, which is also times 2. So if we multiplied the concentration of y by 2, the rate was multiplied by 2, and since it's the same, this means that y is going to be first order. Now, this question is going to be pretty interesting. Pretend you never saw this number, and I asked you, what is this number? So, how do you find that number? Well, let's base it off of row 3. So, for row 3, we know that the concentrations are 0.5 and 1. In row 4, the new concentrations are 0.9 and 0.7. So, that means that both x and y are changing. But the good news is that we already know what x and y are, or in other words, we know how much the rate will change depending on the concentration change. So from 5 to 9, we are multiplying by a factor of 9 over 5. And from 1 to 0.7, we are multiplying by 7 over 10. Now we know that x is second order, so the rate will be multiplied by 9 over 5 squared. Now we know that y is first order, so if we multiply the concentration of y by 7 over 10, this means that the rate will also be multiplied by 7 over 10. So both of these things are happening at once, and multiplying these two together, I get that the rate overall will be multiplied by 2.27. So since the rate here was 4, I have to just multiply it by 2.27 to get the new rate. So the new rate turns out to be 9.1 molar per second. So that's how you do these types of questions. And now let me ask you something interesting. What is the overall order of the reaction? Well, 2 plus 1 is 3, so the order of our reaction is going to be 3. Now, I want you to find the K of the reaction with correct units. So, in the last video, I told you how rate constants can be calculated from the rate law. So, rate is equal to K times x squared times y, and we wrote this because we now know the full rate law, because we know what K is, we know what the orders are, and that's all we need to know to find the rate law. So that is known as a rate law. And in a rate law, you don't have to know what K is. You could simply put K as K. But if you want to go one step further, you can make this rate law more accurate by finding what K is. So I used row 1 to fill out the data. So we know that in row 1, x and y were 0.5 molar. And we knew that the rate was 2.0 molar per second. And doing the math, we get that 2.0 molar per second is equal to K times 0.125 molar cubed. I just combined all the units and numbers, and then I divided both sides by this number over here, and then I got 16 molar over molar cubed times seconds. So of course, you can simplify this using some math, and I get that K is equal to 16 over molar squared times seconds, or 16 molar to the negative second times seconds to the negative 1. So this would be the official answer. And notice how I calculated the rates by paying attention to my units. So let's now try to learn how to find the order of a reaction given a concentration versus time data, either in the form of a data table or in the form of a graph. So from the last video, we did a lot of this. We learned that for a zero order reaction, the concentration of A versus time, where the concentration of A is on the y-axis and T is on the x-axis, we know that that is linear. For first order, it is going to be ln A versus T, and that will make it linear. For a second order reaction where there's only one reactant, then 1 over A versus time will be linear. And for second order reactions where there are two reactants, each with first order and starting at a different initial concentration, you want to graph the natural log of B times the initial concentration of A over A times the initial concentration of B versus time, and this will give you a linear graph. And note that the subscript F is going to be optional, since anything that's not the initial will be something that's after, and something that's after could be the final, or it could just be any concentration after T amount of time passed. So technically, you don't have to include the F when you're referring to arbitrary concentrations that change over time. So, yeah. Now, what we will do is that we will manipulate our concentrations so that they produce a line when graphed against time. So if we manipulate our concentrations and we find that the natural log of the concentration of A versus time graph is linear, then we can conclude that the reaction will be first order. So there's actually a disclaimer. This method only works if the concentration of the substances you are graphing is the only thing causing the rate to change. If another concentration that is not zero order is also changing significantly, it can impact the overall rate. The substances you are graphing won't be the only thing impacting the rate if this happens, so the data of the concentration of the substance that you're graphing changing over time may be messed up and complicated because it involves changing concentrations of other substances shown on the graph. Therefore, scientists like to do a method known as swamping, where they make one reactant so high in concentration to the one we are graphing that it essentially remains unchanged, allowing us to be confident that the rate is changing only because of the substances we are graphing or focusing on. So, this method is very useful, and it allows us to find the orders of reactants while keeping the other reactants out of the way and not interfering with the data. So, now that we're done with this, let's actually look at how we might do this. So, for the products, we are going to assume that the products are zero order, and we have to determine the order of NO2. So, before we begin, I want to mention something. For a graph to be linear, it, has to be a line, or each increment of time must correspond to a constant increment of value. So, for example, for every 2 increments of time, the molar goes up by 1. For every 2 increments of time, the molar goes up by 1. So, the increments of time must correspond to a constant increment of value. So in this table over here, I actually calculated the concentration of NO2, the ln of it, and the 1 over the concentration of NO2. And by doing that, I could find which one of these will produce a linear graph and will allow me to determine the order. So, for it to be linear, the increments have to correspond to increments on the other side that are always constant. So, in this case, from 0 to 50, it's an increment of 50. From 50 to 100, it's another increment of 50. But from 100 to 200, it's 2 increments of 50, or an increment of 100. So, each increment of 50 should correspond to the same increment in order for it to be linear. So we are graphing time on the x-axis, and now we need to figure out what will be our y, and which one of these will give us a line. So let's try zero order, which will be NO2. So we see that from 0 to 50, of course, the time increases by 50, and the concentration decreases by 0.0337. Now we do it again, and is the increment the same? No, it changed from this number to negative 0.0182. Now let's try that again. If we go 2 increments of 50, that means that we should have 2 increments of negative 0.0337, but that's not the case. Instead, it's actually 2 increments of negative 0.0095 or negative 0.0189. So as you can see, the increments are not the same for the same increments of time, and because of that, this should not work. So this reaction will not be zero order, because if you graph the concentration of NO2 versus time, it won't be linear since the increments do not match. Now let's try graphing ln of NO2 versus time and seeing if that will be linear. So for every increment of 50 seconds, this decreases by 0.363, and another 50 seconds, it decreases by 0.273. Now wait a second, that's not constant. And if you look even further, you can see that from 100 to 200, or 2 increments of 50, it goes down by 2 increments of 0.197, or a total of negative 0.393. And that means that the increments are not constant, so that means that if you graph ln of NO2 versus time, it will not be linear. Now what about if we graphed the inverse of NO2 versus time? Well, for every increment of 50, our 1 over NO2 increases by 4.1, another 50, another 4.1, and if we do 2 increments of 50, we get 2 increments of 4.15, or a total of 8.3. So it looks like for every 50, we are going up by 4.1 around, and because of that, I feel like this graph, if we graph 1 over the concentration of NO2 versus time, it will produce a linear graph because the increments are constant throughout the process. And because of that, I believe that the order of NO2 is actually second order, since the graph between 1 over NO2 and time will be linear. Now, you could have done all this just by graphing it and seeing that these two will produce curves, while this one will produce a line. But of course, my method is a lot quicker, especially if you don't have graphing paper on you. Now let's talk about using the integrated rate laws that we learned. So, let's find the time it takes for substance A to go from 1.0 molar to 0.30 molar, assuming that A is first order, and the rate constant is 10 seconds to the negative 1. So, we know our integrated rate law for first order, it is that. We know our initial concentration, 1, and our final concentration, or the concentration after time t, that's 0.3. And we simply plug that in here, and we set that equal to k, which we found was 10 seconds to the negative 1 times t. So we need to find the t. Doing the math, we get 3.3, but I added an extra sig fig for accuracy, and I underlined it to make sure that we have 2 sig figs here. And we took the natural log of that, and 2 sig figs means 2 decimal places, so we have 2 decimal places right there. And we set that equal to that, and we simplify it by moving this to the bottom by dividing both sides by 10 seconds to the negative 1, and that's equal to t. And we find out that the time it took for this to happen was going to be 0.12 seconds, and notice how there are 2 sig figs, since this is 2 sig figs and this is 3 sig figs. So 0.12 seconds is our time, and the units all worked out because dividing seconds to the negative 1 will give you seconds, because if you move it back up, the negative exponent becomes positive again. Now, I want to show you what half-life is. Half-life is the time it takes for half of the reactants to disappear. So in other words, a concentration of a substance A becomes 1/2 of what it originally was. So I want you to find the equation for the half-life of a first-order reaction, because the half-life of a first-order reaction is constant. Knowing this, I want you to find the equation, and let's get to it. So for here, we have our integrated rate law for first order, and I simply plugged in initial and final here and here, and I set it equal to kT. And I know that these two cancel out since they're the same, and I get ln of 2 is equal to kT, and ln of 2 is 0.693, or around there, and I divided both sides by k, and I get that t is equal to 0.693 over k. So this t has a special name. It's actually t subscript 1/2, because it's the half-life, which is the time it takes for half of the reactants to disappear. So in this case, the time it takes for half of the reactants to disappear or be consumed in a first-order reaction is going to be 0.693 over k. So it only works for first order. For every other order, you have to use the integrated rate law and do it from there. And yeah, so radioactive decay reactions occur when an isotope changes into another isotope. They are typically first order. Now, we will learn about isotopes in a future video, but simply a radioactive decay reaction occurs when something like uranium-235 decomposes into something like thorium-231. So you see that the isotope and even the element is changing. Now, I want you to find the rate constant K if the half-life of uranium-235 is 700 million years. So we are going to use that equation we just learned 0.693 over K is equal to the half-life for a first-order reaction. So 0.693 over K is equal to the half-life, which turns out to be 700 million years. And doing the math, I get that K is equal to 9.9 times 10 to the negative 10 years to the negative 1, since it's a constant. And we need 1 sig fig, so we have to actually round this up to 1. And we get that the true answer with sig figs is 1 times 10 to the 9 years to the negative 1. So it's weird how we're using years instead of seconds, but sometimes it takes so long that you just have to use years instead of seconds. Now, as you might have noticed, the lower the rate constant, the slower the reaction. For example, this reaction, which has a half-life of 700 million years, has a rate constant of 9.9 times 10 to the negative 10 years. Like, not even seconds, but like years. And that just tells you how slow the reaction is. So, for the next thing we are going to do, we are going to try to read graphs that are linear and are derived from the integrated rate laws that we did in the last video. So this is a graph of 1 over the concentration of carbon monoxide on the y-axis, T in seconds on the x-axis, and notice how I gave you an equation. I said that 1 over the concentration of carbon monoxide is equal to 2801T plus 205. Now this should be useful information. So, we know that the second order integrated rate law is this. And why second order? Well, when we graphed 1 over the concentration versus time, it's linear, so it's second order. So moving this around, we get that the equation of the line above is actually this, which is the y, and that's equal to k, which is our m, or slope, times our x variable, or t, and we add a y-intercept, which turns out to be 1 over the initial concentration of substance A. So the first thing you should note is that, of course, the final is optional because you don't actually have to include that when writing it, such as over here, where I didn't include the final because that's kind of optional and it's just there just if you prefer it. And in addition, doesn't this equation look just like this, where this is y and this is m and this is x and this is b? Well, yeah. So let's try to extract some information from the graph. We want to know what the K and the initial concentration of carbon monoxide is from the graph and the data. So we know that the K is equal to the slope as shown here, since it's next to the variable t. So since K is 2801, then, K is equal to 2801. But we need units. So since this is a second order reaction, I know that rate is equal to K times the concentration of A squared. I substitute things for units, and I do some unit analysis to find that K has the units molar to the negative 1, seconds to the negative 1. And if you don't understand this, I highly recommend you review unit analysis in the very first unit of this YouTube channel. So we know that these are the units, and you simply just put it next to 2801. So K is equal to 2801, m negative 1, s negative 1. Now, what about the initial concentration of CO? Well, we know that the y-intercept is equal to 1 over the initial concentration of carbon monoxide, and we know that the y-intercept is going to be 205. So 205 is equal to this. So we just do that, and doing the math, we get that the initial concentration of carbon monoxide is 0.00488 molar. Now, remember, this is a method that is not only used for second-order reactions. This method of reading graphs can be used for any of the orders that we learned about, specifically 0, first, and the 2 types of second orders, even though the last type of second order might be a little bit complicated. So, that's all for this video. Have a wonderful day, everybody.